they are interested in. That's how they carve it out from nature. But that's not all that happens. There's more at stake, as I will show. So I will talk briefly about what we mean with Earth system. I will also talk briefly about how this relates to reductionism and vitalism, because that's a tension that we're looking at. And then very briefly about where Earth system thinking originates. I'm also working on that together with historians at the moment. And I'm going to ask for a little bit of help at the end of this talk to some of you who might know something about it. And the main part of my talk is about nearly decomposable systems, what they are and how we decompose them. And I'm going to show that, in my opinion, we are doing 4 kinds of decomposition. I'll illustrate with a model from my field and with the community Earth system model. And then I'm also going to talk briefly about consequences for the Earth science curriculum, where we use the word system quite a lot, but we're not really teaching systems, and that needs to change, and that is something where this community may come in. So, System Earth, what is it? It's about connected spheres, it's about water, the hydrosphere, it's about ice, it's about the atmosphere, etc., etc. You know this. The funny thing is, though, that if you look at Earth system models, they are all basically about Christmas balls. They deal with the outside of the ball and nothing on the inside, while it's clear that the volcanoes are actually part and parcel of the system in the sense that they create atmosphere and they are linked with the inner workings of the planet, plate tectonics. So we really would need a crystal ball that incorporates that rather than a Christmas ball in this case. And now that we think about it, where does the energy come from in this system? It's an open system, obviously. There's also the sun. And the sun is not part of system Earth, and yet it's very important for it. It's a solar system. So that raises the philosophical problem that we're looking at a system, but it's far from closed. It's actually part of a bigger system, and there's also other systems within, etc., etc. And that then leads to questions about emergence and how we carve out this particular system, build a model for it, while ignoring all those other things. That's the question. And it's not just that this model is now Christmas ball rather than crystal ball. It's also that we have a very long history, a dynamic history of contingent events. It's clearly not predictable. Lots of catastrophes happened. And this is what the Earth scientists all talk about, but not in the context of unpredictability of complex systems. And that is also something that we may need to change. So what do we mean by system? And you all know that systems as a term are extremely popular also by managers for like words, chaos and self-organization. Everyone uses those words. Well, what does it really mean? Apparently, victory goes to the business with superior systems. So that is very good news for this group because it means victory for all of us, right? But it's also a very old term. Systems derives from Greek, and there is Hesiod, a very old thinker, 3,000 years something ago, and he says that we actually want to do things systematically, and disorder is our worst enemy. So is he the first systems thinker, or is he a case of OCD, an early case? So more seriously, we call everything a system, and that's confusing, that's problematic for someone with a philosophical mind. So for example, we have systematic knowledge. Think about taxonomy of species. Think about the first encyclopedias in the 1750s by Diderot and D'Alembert, where they systematized all the available knowledge alphabetically. What on earth does the alphabet have to do with the rest of knowledge? And then there's also these other examples, right? We call everything a system. But what does it mean? And that's the task that philosophers take on themselves. They ask the questions, what on earth are we doing? And they study what the scientists do and what they mean and clarify what it must mean and cannot mean. So I stepped outside my role as a scientist and inside the role of a philosopher, like I've done some time ago. I'm redoing it now in order to self-reflect on what our field is doing. And I'm doing this together with philosophers in order to avoid that I'm doing stupid philosophy, which is the risk. A little bit of an introduction about the problem then. Living organisms are seen as systems and have been seen as systems for a long time. Von Bertalanffy, he worked out the general systems theory, as probably all of you know better than I do. And he worked mostly on living organisms to begin with. The growth of organisms was his main target and limits to growth. And the point of it was that he saw that the mathematical formulation of his general systems theory was similar in form if he looked at social and economic systems and many other systems. This isomorphism, the similarity in form, is something that he used to build a more general systems theory. And parts of it come from the thermodynamics, and it's of course all about collective behavior of parts of a system. And the crucial point that he is at pains to point out is that all this is neither about reductionism nor about vitalism. I'll come back to that in a minute. Vitalism is of course the idea that species are more than just a collection of what they are. And reductionism is the idea that everything can eventually be reduced to physics. So if it's collective behavior, does that mean that we can't decompose the system to study how it works? Because if you decompose it, it no longer works. And the parts themselves don't tell us much about how the collective behaves. Possible behaviors, you're very well aware of. There are also all kinds of things that systems do and that are innovations of what we thought previously to systems theory a century ago. This is also, of course, related to the term complexity and not simple predictability. I'll give an example of that. So there is a tension here between reductionism and vitalism. Where are we? A system is basically an organized whole. It's about how it all hangs together. But what is it that is more than the sum of parts? Is it just a sum of causal relationship? Or is a system just a holistic perspective? And the problem is that vitalism says that living organisms fundamentally differ from non-living entities. And that's where the idea comes from that our soul weighs 21 grams. That's the vitalism for you. More formally, we can define a system as follows. It is the mechanisms and entities that are organized such that they produce emergent behavior and phenomena. And then the question becomes, does that mean it's not reducible to the underlying mechanisms from which it's built up because it has emergent phenomena? And how do we isolate subsystems if system properties are then lost by the carving apart? So how do we carve nature at its joints? This is different from the reductionistic ideas that people had in the 1920s and also before and after that, where all the sciences are eventually reduced to physics. That was the idea, right? We have all the cosmology, geology, and geomorphology goes through chemistry into physics. And if you have managed to explain everything there is, then you have done a reduction to physics in the language of mathematics and logic. This was what they thought. And likewise for the life sciences, which raises all sorts of problems, because how on earth are we going to explain the behavior of a mob of soccer supporters by the laws of quantum mechanics? But that was the idea of reduction, physical reductionism. And this is where the saying comes from: science is physics and the rest is merely stamp collecting. But then there's also good reasons to think this, right? The success of reductionism is enormous. There have been lots of explanations from all kinds of phenomena with the reduction to physics. Physics is a very powerful explanation for many things. But then there is this. Is this stamp collecting? This is a map, how it all hangs together, of species, air pressure, visibility on a volcano. It's drawn up by Alexander von Humboldt as the Tableau when he went up the Andes to study vegetation patterns and all kinds of other patterns. And he put them together, and that whole, that was his way of looking at the world, the sort of holism. And that's what he wrote up in the Cosmos and the Plant Geography books. And he says this. He says that science can only progress by connecting it all together. And he talks about a great chain of causes and effects, and the fact that no single fact can be considered in isolation. And he also talks basically what amounts to system properties, a general equilibrium. Okay, we know it's not an equilibrium anymore, but he talks about a general equilibrium, and he talks about it's a result of an infinite number of mechanical forces and chemical attractions. In other words, he describes how it is in principle related to physics, but you cannot really reduce it to physics because there's an infinite number of variables involved. There's too many particles. That's the problem. So what you see here is that already in 1807, he uses somewhat reductionistic slang, because the predominant view then was Newton, but he's really said holism. So that leads to the question, should we actually look at Gaia's theory, right? A lot of Earth scientists often get chased by the ideas of Gaia. The problem is that Gaia supposes there's some form of future orientation in it. This whole Earth system evolves such that it becomes better for the life forms on it. The life forms have taken a hand in the development, the evolution of the planet. And that tendency is there everywhere in Lovelock's work. You can even see it in Tim Lenton's work, who was a speaker recently. And I don't like that one bit, because future orientation suggests there's a sort of agency, which is a belief. It's got nothing to do with science. We don't have that kind of agency. So this is where I carve off that idea with Ockham's razor. So what happens then with Earth system science? Did it originate with Gaia theory? I don't think so. Is it there already in Hutton, the foundationer of Earth science, or in von Humboldt, or in Darwin? I don't think so. I don't think it's as simple as having one hero who did it all, like you have Newton as the hero, which is also not true, because many and many others contributed to the building of physics. So it's a haphazard development of science. And one element in the story is that at some point after the World War, it became possible to do three-dimensional global models for atmospheric circulation. And here you see the famous climatologist Hansen, and he made that model possible well before Gaia theory developed. And that's one element in the development of Earth system science. And already in 1962, well before Gaia's theory, there's this perfect image of systems in Rachel Carson's famous book about Silent Spring, when the pesticides were killing all the birds. That was what she was writing about. And she speaks about a complex and highly integrated system, which we cannot ignore. And she also talks about the balance of nature, which is not really something fixed. It's constantly adjusting, it's constantly changing. So this is clearly, very clearly, systems thinking. Many systems theories were around. There's actually not a single theory. There was a general systems theory from Bertalanffy, and there was dynamic systems theory, and there was also cybernetics, which evolved out of the killing machines developed in the Second World War, which had to move on their own in order to do their killing, and all that work has evolved into electronics and that sort of thing. So there's a lot of systems theories. It's not really clearly a unity. So unraveling the history is difficult. I'm trying to trace now how it went through history, whether it began with von Humboldt and how it came in the earth sciences. I'm thinking that it had nothing to do with the development of earth sciences, but it went through biology or something. But this is work in progress. Now on to the core of what I would like to tell you, namely the nearly decomposable systems. What we do when we study a system is sort of reductionistic. We break it down into working parts, which also clarifies the organization of the working parts and hopefully helps us understand how then the emergent behavior comes about. That is what I mean by decomposition. But you'll know that if you peel apart a living cell, then it no longer is living, it's dead, and you can't really see anymore how it's working. Or can we? So there's this concept dating back to 1962 by a guy named Simon, who also worked with and spoke with von Bertalanffy and many others in that time. And he says that many systems are actually nearly decomposable. There are interactions among subsystems that are weaker than within the subsystem, but not negligible in the long run. Now that is complicated, so I will explain it a bit more. What do I mean? A nearly decomposable system, it has subsystems. If it has subsystems, then what we see is that there is weak interactions between the subsystems, and they are weaker in the sense that the short-term behavior of each subsystem is sort of independent of the short-term behavior of other subsystems adjacent to a particular subsystem, right? So they are doing their thing, and the coordination will come later. That's actually what it means in the long run. Once they have done their thing for some time, they start to coordinate, and then it becomes a bigger thing with emergent behavior. There are many ways you can think about it. You can many examples possible. For example, that living cell with the organelles in it, but also the orchestration of various organelles that are doing the circadian rhythms, our day and night rhythms in species. It has several components in living organisms, and in the end, they coordinate together, even though they do their own frequency of stuff, nearly independent from the rest. And this is what it means to be nearly decomposable. Now, if we look at geosciences, what they say about their systems is that it is related to a certain spatial and time scale. And you will see many, many papers that plot time and space related like this. Many of the interesting problems, many of the interesting changes in the earth sciences take place in that purple band. At a certain spatial scale, we see certain changes over a given amount of time. And if we look at the smaller scales, it goes faster. And if we look at the larger scales, it goes slow. So that this is a very important way to say where we are in the system. But of course, it's not independent. If we're looking at the entire Earth or a volcano or whatever, it's still consisting of sand, molecules, and particles and all that. We've just carved that off. And likewise, the solar system is not part of that volcano if we study a system called volcano. So what we do is actually have a different name for the short-term and long-term dependence thing of the near decomposition. That is what the geoscientists do, I think. They say by focusing on a certain phenomenon, I'm carving off the shorter-term and the longer-term dependencies from my system. I think it's nearly decomposable by that. That's what they're doing. I'll give another example. There's another way of doing this, and that's well known from biology. We can divide up by hierarchies that are recognizable, for example, in cells, organisms, ecosystems. That's what we mean by hierarchies. And the point of doing that actually is that if we look at an organism as a whole, we can ignore the incredible number, the very large number of cells and the even much larger number of molecules. It would be impossible to deal with all the molecules in a model. And what we do instead is deal with whole organisms, because then we can actually study it. So it's effective to do this, to look at the hierarchy. And the fact that organisms actually do stuff to attain homeostasis, to attain constant conditions to stay alive, it actually means they are nearly decomposed from the environment. They protect themselves against all the influxes from the environment. They want to stay constant regardless of what happens outside. So the hierarchy of organization at different scales in nature is helping us to carve nearly decompose Earth systems, for example, with ecosystems or organisms. This is yet another way of looking at the nearly decomposable systems, and this will also come back in the example of systems modeling. We can look at a nearly decomposable system as a network of causal interactions within the system, which is the green circle around it. And then within the system, we have subsystems that have many causal interactions, and other subsystems are also connected together by many interactions. And then between them, there are few causal interactions. So this is where we can ideally carve them up. Now, if we didn't do this sort of systems view, we would have an incredible number of molecules or atoms or whatever involved in this. So organized complex systems, the fact that they are organized means that we have the astronomical number of variables, atoms, molecules, aggregated in larger working parts. And it's the larger working parts that we're looking at. And also, if there are interactions within the working parts that are stronger, it's all the red connections, then we have subsystems, and then we can carve them out from the other subsystems, even though on the longer run there's orchestration. So this is yet another view on what nearly decomposable systems are. So we have 4 ways of being nearly decomposable. And I'm doing this, my purpose here is that we understand what we do in practice with our systems, with our models, right? And the earth scientists already refer to long-term and short-term. We know that the biologists already refer to hierarchy quite a lot, and earth systems inevitably have life in them. But there is also this idea to represent a system with a causal network representation. And I think many of you are actually doing that mathematically. And that is, of course, about the furniture and the architecture of the system. So my claims here are there are 4 kinds of decomposition, and this clarifies a lot of the practice of complex open Earth system modeling. It tells us how we recognize systems, how we sunder them from the environment, carve them out, and how we study them. And I'll now give examples. Because the Earth simulation models actually show us how Earth scientists recomposed their systems from those working parts. So it tells us also how they thought to decompose the real world into subsystems. I'll show you with 2 examples. The first is a model I helped build myself. We used the Delft 3D model, which does surface flows of rivers or coastal seas or river mouths. And it does sediment transport, sand and mud is being transported by those currents. And that changes the shape of the Earth and the waterscape, the landscape and the waterscape. And that in turn changes the flows over it. So this is actually a model for developing a landscape. However, it is really lifeless. It's all about sediments. So this existing model from Deltares is carved out of the world, really, because it is a piece of the world that we run it onto, and it has initial spatial conditions, which means it has a longer term history that's basically put into initial conditions, the initial landscape, but it also has smaller scale processes, the time-dependent boundary conditions from climate and the parameterized processes in it. We made this model alive. That was my research group. We put in eco-engineering species. And they are species that change their environment such that the environment becomes better for their own species and sometimes also for others. Think about willow trees who build landscapes, lead to sedimentation. But think about beavers who build dams. And actually, this funny symbol at the bottom of my presentation, which is part of my format, shows a river with sand around it. It shows trees, and it even shows a beaver dam there upstream. So what we're doing is calculate where species are going to sit on the basis of physical habitats. We run them through their life stages of settling, growth, and various kinds of horrible death. And then they have, through all this, engineering traits. They affect the physical environment. So this model we built, and we coupled it with Delft 3D. So the hydrodynamics and the substrate, meaning sand or mud, determines which species sit where. And then once these species develop all their ages and the seasonal cycles, etc., they cause resistance to the flow. They cause the bioturbation and stabilization of the soil. And they even cause peat formation. They build the landscape. In fact, they build the half of the Netherlands. That's also why we're interested in it. This is an example of the output for an individual single river. On the top plot, you see a map. Where the river goes, it's blue, that's deeper. And the green says where the vegetation sits and what age it has. And I point out that this paper is open access and has beautiful movies, so you can go and look at it. So here we have a coupling between plants, sand, mud, and water that are doing a very dynamic landscape. So it's a complex phenomenon. It creates a meandering river that would not emerge without life. You would have a braided river instead. Moreover, we see very interesting time-dependent behavior that is far from stable and simple. Here I plot mud cover versus vegetation cover for the average model, and then we see all sorts of cycles going in as you go through time, which is here represented by color. Which is really funny, because we tended to think that where the vegetation sits, we also have mud. It's not so simple. What is it we did with this system? We carved out a window in the space of time scale and spatial scale. That is really what we did. My model is within that window. You can see the flow, erosion, sedimentation, riverbed cycle there. You can also see the connections with vegetation. But this is only part of the time scale and spatial scale space that we have. What we did was carve off the larger scale and the longer scale dynamics of plate tectonics that made the valley where the river sits anyway. And we put that in its initial conditions. We carved off the boundary conditions, which are very fast varying things, the amount of water and sediment coming in and going out. And we also carved off the smaller scale processes that we're not incorporating in the model. We parameterize things like turbulence and how that happens around plants and particles. And we also carved out the evolution of the plants that evolved from very simple things without roots to things that can actually survive along rivers. Plants evolved with the river since about 524 million years ago. So also that much longer time scale is now carved out from the rest of the universe. Furthermore, we have done a sort of hierarchical separation here. We have separated the physics and biology. They are in a living apart together relation of feedbacks. This means that the system here that I'm showing is decomposed and recomposed in the model in three ways. Smaller scales are carved off, that's one. Larger scales are carved off, that's two. And we have separated out the living and the lifeless stuff hierarchically, and also made them into separate subsystems. That is what we did. That is how I can describe what we did. So how do we do it? Models show that how Earth scientists actually recompose systems. We have these four windows, time and spatial scale, that disentangle the system from the microscopic world and the solar system, even though we know that in the long term there are connections. It also separates out sub-mechanisms by hierarchical levels, physical, chemical, biological, you name it. And that leads to the question, what else we do? And now I need to go to a more complex system. This is the classic plot graphic of Reducto. It's the first climate system, if you like, developed by NASA. Now what he's showing here is a connection between the physical and the biological. So he's doing the same thing. The top bit, blue, is physical climate system. The bottom bit is biochemical cycles. He's also separating out volcanoes and the sun on the left as external forcing. So he's doing the crystal ball approach here, right? But also he's separating out human activities on the far right, which is also interesting. So he's carving that off our present system. And this was a fairly simple representation of Earth system models. And since then, people have drawn up much more complicated pictures. Look at this one. This year in Nature Reviews Earth and Environment by Stefan et al., including I think also Tim Lenton. And what they did was draw up a very complicated diagram, which has a geosphere, which is physical, a biosphere, which is biological, and an anthroposphere. But look carefully at this. In the biosphere, we have mixtures of biological and physical stuff going on. And there's more funny things. Look at how many arrows there are, kinds of arrows, so many different kinds of arrows. And then we have this. We have extinctions, energy systems, we have vegetation. Extinctions and vegetation, they are on very different timescales. Extinctions, they happen on timescales of millions of years. Vegetation, seasonal. Energy systems, that's a subsystem, that's a different system. And also look at this, the volcanoes and the fossil fuels, they're taken out of the system, but fossil fuels are obviously something that are part and parcel of the anthroposphere. So what is going on here? They've drawn a diagram, but is this really how they model it? I doubted that. So I wondered, is it really this broad range of timescales? Do we have all that? Are there really 9 kinds of different arrows? Do we really have these volcanoes outside the system? Is the geosphere really mixed up with the biosphere? So I looked at the Community Earth System model, which is open, online, it's available, it has manuals, it has open source code, and that was an easy thing for me to delve into. And this is how they represent it. You see boxes of submodels, if you like, that are coupled together for all those parts of the Earth system. So this was interesting to start. And then if you look in their documentation, the manual for the community land model, which is only one part of it, then we see this. We have on the bottom a sort of geographical thing, which mixes biology and human things, but also hydrological things. It's all put there together. There's even a special vegetation dynamics model, which is again a subsystem. And then for each and every grid cell, they also have mixtures of things, right? That's the top drawings. For example, for hydrology, there's clearly soil, and there is all kinds of evaporation and transpiration and infiltration, that sort of hydrological thing going on. There's also life. Likewise, for the energy fluxes on the top left panel, there's interaction with the soil, that's biochemical, if you like, and with the plants on top of it, and the physics. It is not easily separated by hierarchy, and it has multiple scales mixed up together. That is what we're seeing here. So, this is a very simplistic representation of that community land model. And I think the atmospheric model and ocean models have their own complexities within them. What we're seeing here is a mixture of all kinds of levels in scales of time and space, but also in these hierarchies of physics, chemistry, biology. So this is really a nearly decomposable system. We have subsystems identified with many causal links within the subsystems and fewer causal links between the subsystems, but it's not carved up by hierarchy. Many of these subsystems are actually multi-level, so that makes them very complicated, and the only way to look at this is from the perspective of a network of causal interactions. So how do we compose complex open systems in practice? We have this time and spatial scale, we do hierarchical levels, and if all that fails, if nature forces us to build better models by making them integrated in hierarchical levels, then we end up with an organizational architecture wherein we hope to be able to recognize subsystems, and then we carve between clusters of these interlevel relations. That's our plan C. That is, in brief, what I think we're doing in the Earth system models. So what do we mean by system? It's a perspective, or really a model of a part of reality for that part that we are interested in. And it's organized into working parts, and it collectively causes phenomena and behaviors. But it's not vitalistic, it's also not really reductionistic. That fails. Look at hierarchies. And of course, you all know that Earth system modeling is much more efficient than reductionistic modeling, which is why we do it. And that's really, as we say, an open door statement in Dutch. But the thing is, many of our colleagues and students actually maintain this idea and ideal of reductionistic models. Many people think that if you have a computer that is large enough, you can put the entire system in. And all the people who have read The Hitchhiker's Guide to the Galaxy know that it's actually a joke. This is a model of the Earth, and the only correct model of the Earth is the Earth. Why is that? Because there is such an enormous number of entities and relations involved. Simple causal processes like billiard balls are taking place on very small scales. That's on the bottom left of this plot, and they have only 2 entities involved. But as soon as we look at bigger phenomena, the number of molecules rises enormously. It goes rapidly to infinity. So that's not useful to study the world with our human limitations. So instead, we recognize these clusters of densely causally related processes, and these are the submodels of the community Earth system model. And then what we do is we carve out those connections between the subsystems so that we can study each subsystem separately, and we put them back together by coding their connections in a connectivity part of the code. And this is where we decompose and recompose the code by carving between those clusters that to some degree occur on different scales or on different levels, and sometimes also simply on different architecture of the causal network. This is a complex graph. It's not even correct. It's more a graphic than a graph, really. But I'm hoping that you see what I mean here. So that's all very nice. What to do with it? The most important thing I hope to accomplish is insight in what we do. But then also I would like us to think about what to teach, because we have a curriculum of Earth science where many of our courses are called system something. And if you look at the courses, there is no teaching about systems in it, which is a bit of a pain. So what we are really doing is go systematically through a number of things, but it's not really about the system, right? So where is the systems thinking? Do we only teach linear causal thinking, or is the systems thinking implicit in our teaching? And if it's implicit, shouldn't we do something about it? Because the didactic literature says that we, our students, you, me, we learn better if we know what we learn and why we learn it. So you have to say out loud what it is you're learning, and then you learn it better than when you're just trying to understand what a teacher is doing. So this is about students. Their importance for us is, of course, enormous. We need students, we want students, it's the future. So how do we teach? And it's not so simple, actually. Kerst Boersma, who was a biologist and didactics expert at the Freudenthal Institute here in Utrecht, he helped write a review with his group, and they say, obviously, that the importance of systems and systems models in science education has been widely recognized. Yes, indeed, we even have a focus area, the complexity group here. But there is no consensus on what systems thinking implies. And even worse, how can we foster systems thinking by adequate learning and teaching strategies? How do we teach it such that our students really learn it, other than by seeing and copying behavior? So, my conclusions for our curriculum is that we professionals also need to know what we're doing. And we not always know what we're doing, really, not in terms of the systems. So we need this know-how of our practice for lots of things: interdisciplinary understanding, intellectual development, and lots of fun. But we don't. So we need to implement philosophical concepts in our curriculum to be clearer about what we do and about our claims. And systems is just one of the many wanna-haves, and this is work I'm doing with the Director of Education for our program. And I could use some help with that, actually. So I'm coming to the end. You can see this is slide number 42. The system is a recomposed model, which is a perspective on the world, on an interesting piece of the world, and we decomposed it from the world by time and spatial scale, by hierarchical levels, and by organizational causal architecture. I could use some help here. How to teach students and colleagues to foster systems thinking. And it's for earth scientists, remember, so they won't be very happy if you dump lots of equations on the head and say, ta-da, this is systems thinking. Because for them, it wouldn't be thinking, it would just be panic. Also, I just don't want us to simply draw diagrams that have no meaning whatsoever. It's just fun for managers to be very divisive about one particular kind of branch. We are natural scientists, so we want the real science, but how to do this? I would love some interactions with you. And also, if anyone happens to know a bit more about the history of systems thinking, I already found more about history since Bertalanffy, since the 1920s, and the history of cybernetics and all that, but I found no clear trace between von Humboldt to Bertalanffy and from Bertalanffy to the Earth system sciences. So that's also interesting to think about it. How did we end up to be thinking about Earth system science? And with that, I've come to the end of my presentation, and I thank you for your attention. I shall now unshare my screen.